Hello. Good morning. Holy cow, Saturday morning. I'm impressed with this town. I'm going to talk about particle physics in general, and a lot of what I'm going to say, in a sense, is old news, old-fashioned. I think you get a lot of questions, especially from the media, about the latest and greatest thing. And of course, the interviewer doesn't actually know the previous 100 to 400 years of physics, and because of that, it's very hard to answer questions like that in 90 seconds. So I'm going to give you some of the older stuff because it's mind-blowing in its own right, and then I'll talk a little bit about some of the speculative things we think about that may or may not be true. But let's ground it in what we know. In fact, let's go way back. The first thing you learn in physics is to mistrust your instinct. What you do is you build intuition over time, but you don't look up and see the sun going across the sky and simply decide the sun is going around our flat surface here. In fact, I would say that this was a key moment, Copernicus putting the sun at the center of the solar system, or of the universe at that time, was you fight your intuition, and once you've written down a theory, then you test the theory. And then your testing has nothing to do with how you feel in the morning. You may wake up in the morning and say, oh my God, that was a bunch of garbage. You don't get to decide that anymore. Experiment decides that. And so this was revolutionary in many senses, but it is mostly that you can now step outside yourself, put the human perspective somewhere else, and then write it down and say something concrete and ask, is it true? We can just ask, is it true? Or is this a better description of nature? The other thing that comes up in physics is that there are things and there are laws. And we need to figure out, when we're looking at something, is it a deep signal from how nature works? Or is it just some garbage that's sitting there and has no rhyme or reason? It comes out for some random accident. And a great example is in the case of Kaplan, who was deeply committed to understanding why there were 6 planets and why they were the distances from the sun that they were. And he had this beautiful model. There are only 5 perfect solids in 3 dimensions, 5 solids where all edges are the same length, all sides are the same shape and size. And he thought if you inscribe the 5 Platonic solids in the correct order, you can predict by the spheres that would go inside and outside of them, you could predict the positions of all the planets. And his theory worked almost perfectly, but it failed. And he was very disappointed. And of course, since then, a 7th planet was discovered, and then an 8th planet was discovered, and then a 9th planet was discovered. And then the 9th planet was demoted, so it's not really a planet. And then there were 14 other things that looked sort of like that planet. And then there's an Oort cloud, which is speculated about. And then there are planets going around other stars too. And it turns out the 6 planets going around the sun at these distances really are an accident. And nobody is working on that today in any serious measure why we have the exact number of things we do around the sun. We are one of many solar systems, and each one has characteristics which are environmentally driven. But along the way, part of what destroyed his beautiful picture of what the solar system was he realized, taking data seriously, that planets didn't go in circles, they went in ellipses. They went in ellipses with the sun at one of the focuses of the ellipse, and that he could actually get equations to describe the simple motion of any planet going around the sun. So the law he discovered was the rule for anything going around any big, heavy gravitational object. It travels in an ellipse, and its longest length of that ellipse, cubed, divided by the period squared going around, is proportional to some number. And that number is the same for every planet going around our sun. And so that was an astounding discovery. It was a law. And what that law means is you don't care about the specific planets themselves, but I can predict if I could create another planet and throw it around the sun, it must follow that rule. And that was driven, both his rejection of his old idea and the discovery of the law is driven by very precise data. And data sometimes leads theory, and sometimes it's vice versa. So this was the quadrant, or a picture of the quadrant that Tycho Brahe used to measure the positions of stars to an accuracy. His goal was an accuracy as a 60th of a degree in the sky, or 1 minute. He didn't quite get that, but he got relatively close. And that accuracy allowed Kepler to throw out his data. I mean, throw out his deep theory that he was emotionally attached to. Here is the new quadrant. It's called the Large Hadron Collider. The Large Hadron Collider, fast forward 400 years later, this is the thing we need to study some basic laws. It's not our fault. It just turns out this is what nature requires to get there. The Large Hadron Collider is an insane project. You can go from the very tiny to the very big. On the small scale, there are many different attributes or aspects of the machine that were required to be developed in order that the machine would work when it was finally installed 20 years later. So first of all, you have to predict how fast computers would be and how strong magnets would be by the time you start installing to get an up-to-date machine. This is a crystal that goes into one of the detectors. As you see, it's transparent. It catches light. It catches things that carry electric charge, but in the visible spectrum, you can see through it. It's 99% tungsten, which is a metal. So this is like transparent tungsten, which is doped a little bit, which is bizarre. That's the sort of thing that goes into this experiment. Different parts of the experiment were constructed much larger than the average human, and many of them had to be trucked in, sometimes through the small towns in Europe in the old days, but they're more sophisticated now. And then they lower them. This is a slice of one of the detectors, and it's being lowered 300 feet underground, which is where the entire machine resides, the Large Hadron Collider. It has to be lowered that slowly because it's a significant fraction of the mass of the Eiffel Tower. And so if you go much faster than that, you don't want to hit the ground at any sort of recognizable speed. Once it's in, of course, they have to install it. And the Large Hadron Collider is this ring. There are detectors at certain points, but it's a ring that accelerates particles to very close to the speed of light. It's 16.5 miles around, and it's instrumented with superconducting magnets all the way around, roughly 7 tons each, and they all have to be attached together perfectly. Within the magnets, there's a tube, which is extreme vacuum. All of the air is sucked out of all the 16.5 miles in that tube, 2 tubes, so you could have 2 beams of particles going in opposite direction and not crashing into molecules of air. The superconducting magnets require, they're basically electric currents, 12,000 amps of electric current going through there, and you need 0 resistance, because you have any resistance with 12,000 amps, everything melts. So you turn them into superconductors, and you do that with tons and tons of liquid helium, which is kept at a temperature just slightly below the temperature of deep space. And then you get data. And to analyze the data, there are over 100,000 computers that are some at CERN, but many of them are all over the world, and they're connected by a grid that the Grid Computing Center at CERN had been developing for decades. And the analysis of the data is done worldwide in parallel on these machines. And there are thousands and thousands of people working on it. This is one fraction of one of the 4 major collaborations. This is roughly less than 10% of one of the collaborations. There's 10,000 people on site roughly at any one time, 2,000 people who work there, and 8,000 people who come in, visit, help out, but are at their own institutions. And they come from all over the world, even countries that don't collaborate on anything else. China and Taiwan, Georgia and Russia, Iran, Israel, Serbia, Croatia, India, Pakistan, Cuba, and the United States all have physicists who work on this machine in one aspect or another. Why? Why are they? What is going on? This seems like an enormous amount of effort to build this crazy thing. Well, I'll answer it. This is our pat answer. We're trying to understand the basic laws of nature. Okay, that seems like still a very dramatic thing to do for something that's prosaic sounding. It's like saying, I'd like to understand how an automobile works, and so I will smash 2 automobiles together, and then I will see what comes out, and that's then that metaphor is attributed to Richard Feynman, great physicist and expositor of the past. I don't know if that may be apocryphal, but that's not exactly fair, but it is true we are the NASCAR of physics. We are the particles, the matter that we're accelerating. We are accelerating things to speeds faster than anybody else accelerates things to. So there's something brute force about what we're doing, for sure. But let's talk about what we're actually trying to figure out. The constituents of matter. This is sometimes, what is all matter made of? What are the basic elements of matter? This is sometimes where people turn to explain what we're doing. We know if you take something that you're used to, like a glass of water, and if you can blow up or examine, say, 10 million times smaller, you would see that a continuous liquid looks like something chunky. It's made of molecules. And so that's a little representation of H2O. And if you go just a little bit smaller, I've skipped many things, all the things I'm not good at, biology and, whatever, contaminants. Now they're H2O. So you go just 10 times smaller, we can focus in on an atom, this is a terribly incorrect picture of the hydrogen atom, but we will go with it. So there's a proton and an electron. So you see already not only there's a smaller structure, but there should be even smaller structure still. And so you keep pushing to understand what it's all made of. So if you look at the electron 100 times smaller, you say, is there structure there? And you say, well, no, 100 times smaller, it still looks like a dot. And so then people became very interested. Well, where is the structure of the electron? You go 1,000 times smaller, and you get a dot. And then you go another 1,000 times smaller. Then you get a dot. And then the LHC goes 10 times smaller than that. And what are we going to see? Okay. Just this is not where you'd bet your money that we're going to see anything interesting. This is part of what the LHC is doing. Is there structure to the fundamental particles we know? But there's more. This is not it. We know matter so insanely well at this point, and we will keep pushing that envelope, but that's not where the deepest mysteries lie. So what I'd like to say is if everything is made of atoms, as far as we know, and we understand everything, then what are we looking at? We're looking at nothing. And we're going to look very carefully at it. And you see, all right, we don't say that to granting agencies, but I'll say that to you. It turns out that nothing is not nothing. There is stuff, which, in terms of the things in this room, are made of atoms, all kinds of different atoms, just the collection of protons, neutrons, and electrons. And then there's the vacuum. The vacuum of space turns out to be extraordinarily complicated. That is the nothing within which matter lives. The things live on top of the vacuum of space, and we'd like to understand what that is. Not just because, for fun. We're doing it because we see that there's a lot more to the mystery of what this universe is living in the vacuum. And the Higgs, and we'll talk about that a little later, is one example of the type of thing that has a significant impact on the vacuum. The Higgs boson was a particle whose discovery was announced July 4th, 2012, and we'll get back to it. Before we get there, I'll talk a little bit about quantum mechanics. You're going to learn quantum mechanics in this talk and quantum field theory. So hold on to your hats. We'll go quick, though. Here's something we understood. There's a thing that Richard Feynman, same guy, said at the beginning of one of his public lectures. He said, if I say something, well, he was giving it in New Zealand. So if I say I speak too fast or have a funny accent, I'm sorry, you don't understand. Please let me know. It's my fault. If I use technical language, which I use every day, but now I'm talking to a public audience, that's a mistake because I'm used to it. I'm trying not to do that, and that's also my fault. But if you watch and I explain something, you say, no, it can't be, that doesn't make any sense. How could that possibly be true? I don't believe it. That's your fault. This is what we found out. And so I'm reporting, and you can either come along and say, okay, this is what they found out. Boy, is that weird. But it's, people have been looking very hard to figure out what's going on, and the answers keep coming back weirder and weirder. Quantum mechanics is a theory that is deeply embedded with theories of waves. You need to know a lot about how waves work to understand quantum mechanics, it turns out. So if you take a little box, a pool of water, and you have sort of wave fronts coming up, hitting a wall, and you only let it go through two little holes, then you get this beautiful pattern coming out the other side. There are places where these circular waves coming from the two holes cancel each other. So you get these stripes where there are no waves, where the water is still, and then in between the stripes, this enhancement of the waves. So waves don't exist at a point. They exist in an extended region, and they can cancel each other. And if you call the thing coming from the other side a single wave, then what goes through the hole is that wave interfering with itself. We've converted it into something that's interfering with itself. Bizarrely enough, light is also a wave. If you do the same experiment, not with water, but a laser hitting two little slits in say, a black piece of paper, then what comes out on the other side are light spots and dark spots. The dark spots are where the two waves, say going like this, perfectly cancel. So you add these two together, you get this. But if you add these two together, you get a much brighter wave. And so you get spots depending on the distance from each of the holes, whether the waves cancel or are enhanced. The weirder thing is that light is also a particle in the sense that if you turn down the light to very, very low intensity, and you have on the back wall, you have something that can absorb the light, say like photographic paper, and then you leave the room for a month and you come back, assuming nobody messed with it, you see these dots. You see these places where the very low intensity light acts as if they're made of photons, little dots, little particles, and they hit the back wall and cause it to light up. It leaves a spot there. And then if you wait long enough, one particle at a time, you still get this wave pattern. There are parts where it's dark and parts where it's light. And then you ask, well, if only one particle went through at a time, which hole did it go through? How did it interfere with itself? It doesn't make any sense, but it does. And it's not my lecture. Feynman's lectures, you can go on the web, they're free. I think Bill Gates purchased them and then put them online for free. So you can go from the 60s, he gave these in Cornell, it goes all through quantum electrodynamics. They're a beautiful set of lectures, but you really need to go through all of them to appreciate it. But it turns out it implies something about all particles. All particles When you detect them, you get the experience that they are a particle, but when they evolve in time, they evolve more like a wave. And so when I say like this, oh, electrons, this is a terrible picture of an electron. First of all, the proton is way too big. But the other thing is that if you say the hydrogen atom in its ground state is an electron going in a circle in some direction, and then you measure how much rotational energy is in the hydrogen atom when it's in its rest state, in its lowest energy state. How much rotational energy? And it's zero. We know it's zero. There is no rotational energy. So it couldn't be something going around. The electron, it turns out, acts like a wave. And we describe it when you go to chemistry, you say there's an electron cloud. And you don't know what the hell that is. But you can think of it as like if you had a glass of water and you sort of hit it on the ground and you get this vibration of the surface of the water. It's like a standing wave. It's stuck. The electron is stuck attached to the proton because of the force, the electromagnetic force, but it's just sort of waving in a way. That's the electron. That's how the structure of the atom looks. There's no rotational energy. It's that. And when you measure it, you send in a high-energy beam, try to hit the electron. It hits it at a point. It discovers a particle. And so we have these two bizarre things. First of all, particles evolve in time as if they're waves. And there's even a more quantitative analogy, which is the higher energy the particle has, the tinier the wavelength is. And so if you want to create very tiny wavelengths or high-frequency waves, you produce very energetic particles. The second thing is that the waves somehow are associated with what we call the uncertainty principle. That when you measure the particle somewhere, the probability you will measure it there is based on the shape of its wave, called wave function. And so that is the interplay between waves and particles. And I won't, that's enough. Okay. Now, let's go back to the vacuum. We build big, giant machine, investigate the vacuum. What are we doing? How are we actually investigating the vacuum? So when we investigate matter, you imagine a microscope and you look through it, and light bounces off the thing you're looking at and then goes into your eye. And if the wavelength of the light is much bigger than the thing you're trying to look at, you don't resolve it. You see just a blob. The light reflects off it, but you can't tell exactly the intricate details of that tiny thing. In some sense, the light itself is too big. You're trying to, investigate something tiny, like say a microchip, by throwing basketballs at it and seeing where they bounce and then describe in detail what's happening there. You can't do that. And so you need something tiny. And what we know is tiny means higher energy. If we want to go to higher frequency or tinier wavelength to investigate tinier things, we go to higher energy. And so light, or any particle, the electron, the proton, at very high energies acts as if it's a wave of very short wavelength. And then you can start to see very tiny things. But how do you look at nothing? There's nothing to bounce off of. And the way you look at nothing, well, let's step back a minute. Let me describe what happens in colliders. Before the LHC, there was a collider that took electrons and their antiparticle, the positron, and they smashed them into each other in the same tunnel. It was a lower energy machine, but this was done millions of times, these collisions. And so here's an example of something that would happen. The electron and the anti-electron go in, and then two different particles come out, the muon and its antiparticle. And that's a little weird, but what's weirder is that the muon is 200 times heavier than the electron. So where did that come from? Well, Einstein provided us with a very nice t-shirt ready equation, E equals mc squared, and really what you're supposed to interpret is that mass is a form of energy. This is not the actual equation. This is the equation which, eyes will glaze over, but this people like, so we stick with that one often. But the statement is that at the very fundamental particle level, you can describe things very cleanly often, where there are only two kinds of energy. There is momentum, that's kinetic energy, the energy of motion, and there's mass. And c, you've maybe heard, is the speed of light in this equation, but c is just a very, very big number for every day-to-day thing that you experience. In particle physics, we often set c equal to 1, just because we get to choose whatever units we want, and so that's what we do. There's a lot less, it's easier to avoid mistakes if you have fewer symbols. So there are two types of energy, and the fact that what we know about the universe so far, especially locally, quite precisely, is that energy, or something like energy, is conserved. The energy before and energy after is the same. But that also means you can convert from an energy due to kinetic energy, momentum, and an energy that is stored in mass. And so you can create mass. But this also suggests that, so then I do a little graphic. See, energy is conserved. So before, there's large amount of energy in the beam and a large amount of momentum. We use P for momentum, not my choice. And then small amount of mass. And then when they collide, you can imagine, I keep doing this. Then they collide, they come out. Now you have produced something with bigger mass, so the mass is bigger. The momentum is smaller, but it's the same amount of energy. But where did the electrons go, and where did the muons come from? I mean, yes, you can create mass, but where is this new thing that came out, and where did the other thing disappear to? So here's quantum field theory. We'll call it lake theory. What is lake theory? Imagine you have a lake, perfectly still surface, not frozen. Things are warming up. And you take a rock, and you drop it on one side of the lake, and then there's a wave. You create this little ring, and a wave goes by. And let's say, due to the properties of this lake, the wave mostly stays together and travels across the lake. And that wave contains energy. You have put energy into the surface of the lake in the form of a wave, and it travels at some speed, depending on the properties of the lake. Is it water? What's the temperature? What's the pressure? And we can call that little wave a particle. We say, well, quantum mechanics, particles and waves are similar. It's a little packet of energy that goes from one place to the other. So what's fundamental here? Well, if I didn't throw a rock in, the lake would still be there, but there would be no wave. If I threw a bunch of rocks in, I'd create a whole mess of stuff. The ground state, the lowest energy state, is a still lake. And in that sense, you can describe things as if the lake, or the field, the thing where the wave travels through, is the fundamental thing. And the particles that can just be created or destroyed. Imagine a sort of goofy situation. You have water, and then deep in the lake, there's a secret surface of molasses. The bottom of the lake is filled with molasses, and then a bunch of water, and then it's all rest and still. And molasses is very thick, requires a lot of energy to create waves in molasses. And so imagine the perfectly set up waves on either side of the lake, on the surface, come together, hit each other in such a way, such a violent collision that it disturbs even the molasses in the deeper lake. And little waves of molasses go out in both directions. This is a way that you could imagine converting one type of wave or one type of particle into another. If you have enough energy in one, you could perhaps create these little packets of energy in the other one. But you need some threshold amount of energy. You need enough energy to create that disturbance in the molasses. Now, imagine that all the lakes are on top of each other. All the surfaces are right there. They pass through each other. So they're not deep or anything. They're all right there at the same time. And you can have a wave going through water and convert it into molasses wave, and the molasses wave comes out, and it can convert again. Again, what is fundamental are the lakes. They are just there. And whatever energy is put into them or taken out of them is the state of matter that we see. And so we imagine space-time sort of looks like this. There's a whole stack of lakes, but the surface is not two-dimensional, it's three-dimensional. It fills all of space, and each of those lakes represent what we would call a particle. If you somehow can put energy into that surface, into that field that fills space, you get out the little wave. And the wave, we measure, it looks like a particle, and we say, oh, it's possible to create that new particle. And we've been trying to figure out what space-time is essentially made of. What are the contents? What are all the lakes that exist that fill space-time? And this is the list we have come up with. Again, we don't know why this is true, but this seems to be what it is. This is a list of, 17 particles. The guy in the middle was the most recently discovered. The E is the electron that's in atoms. The U and the D are quarks, which are bound up to make protons and neutrons. And the other ones are either very unstable or are involved, do not interact in long ranges with matter very strongly. So there are many other things. The other one that would be familiar is the upper left blue, which is gamma, which represents the photon, or the particle of light. And that's it. Those are all the lakes that we have discovered. This replaces the old theory, which is water, fire, air, and earth, which it looks simpler, but mathematically it's much more complicated, it turns out. Now, so the nothing is not nothing. Nothing is, in a sense, the potential for the creation of something. And when we collide things, we're putting energy into a spot, and that energy goes in, touches the vacuum in a sense, maybe metaphorical sense, and then what comes out is a reflection of the vacuum. You send something in, and you see what the vacuum is made of. And by putting energy into it, you get the ripples, which we measure and interpret as particles. And the Higgs is one of those things. Let's see. Okay, I like these pictures better. What is a field? I say field. The word field, I say it's something that fills all of space. It's not something you feel. It's not something you pass through. It's a property, in essence, of all space. But you've experienced fields. If you have a magnet, and you say you have two magnets, and you put the same end towards each other, you feel a repulsion between them. They don't touch each other, but you feel something. That can be described as a physical field that surrounds the magnet. The magnetic field can be very clearly mathematically described. It gets weaker as you go farther from the magnet. It has a direction associated with it. So the South Pole and the North Pole are different. And if you take two magnets and bring them near each other, it changes the shape of the field. So you're doing something physical there, and that's why you feel a force. And so the magnet becomes a source of magnetic field. It turns on the magnetic field around it. There's a dormant magnetic field everywhere in space, but this allows you to turn it on, and then you feel the effects. It's stronger in some places, weaker in other. It therefore has a direction associated with it, and that gives you a force. We think the Higgs field is just like that, in a sense. It's a field that is turned on, and the difference is we think the Higgs field is turned on everywhere. But if the Higgs field's turned on everywhere, there's no preferred spot, there's no direction associated with it. It's the same everywhere in space. And so what can it do? The Higgs field instead can give what we call mass or inertia to elementary particles. Mass doesn't have a preferred direction, it doesn't have a preferred location in space, but once a particle has mass, it has inertia. It requires energy to accelerate it, to get it going faster. And it turns out that particles that do not have mass, and there are particles that do not have mass, the photon doesn't appear to have mass. Neutrinos almost didn't have mass, but now they have mass. So forget that one. But if they didn't, any particle that does not have mass goes the speed of light. It just turns out. This is a rule. It's the law of relativity, and it seems to work out. The photon goes the speed of light, and anything which has an energy much greater than its mass goes very close to the speed of light. So that's the limiting speed, and if the electron, for example, had no mass, it would whip by the proton and it would keep going. You would not be able to trap the electron in atoms. So just for a very practical reason, it's very good that the Higgs turned on everywhere. Now the electron has a mass, and it actually can get trapped with the proton and create an atom of some finite size, and they can stick together, and you can get macroscopic professors giving public lectures in Ann Arbor. Just to be a little bit more accurate, here's a couple of photon particles coming out when the electron gets trapped. It loses energy as it gets trapped, emits them in the photons, and because it has less energy, it doesn't have enough energy to escape. It's no longer at escape velocity, and so that's the creation of atoms, as we think happened when the universe was roughly 350-odd thousand years old. The Higgs particle, the wave, we had a big enough rock at the LHC to splash and confirm, yes, there is a Higgs field, and we've seen the vibration in it. We've seen the Higgs particle. So there's a data set. There's another data set. You look for a bump, something coming out at a singular energy, E equals mc squared, meaning you're seeing a particle of a single mass. A new particle that's not what is expected from the rest of the standard model, and then you celebrate. And that was good. Very rare. Particle physics gets on the front page of the New York Times. The other time was when people thought we were going to create a black hole that would eat the Earth. So sometimes it's good news, though. Yeah, it's all okay. What other fields could we discover at the LHC? The LHC is shut down now for roughly a year. It will turn on. Predicted is next February at higher energy, a bigger rock. You can splash it into thicker lakes if there are any down there. So what could we discover? One particle we could discover potentially is a particle called dark matter. And I don't have time to talk about it. I'm sorry. I will talk about it a little bit after the movie on Monday, if you happen to come to that. But dark matter is something that they do look for at the LHC. It's quite complicated to look for it at the LHC. But another question we're trying to answer is, what gives the Higgs particle itself a mass? The Higgs field is responsible for mass for a number of the particles in the standard model. And in a sense, the Higgs interacts with itself in a way that you could say, well, the Higgs gives itself a mass. But not really. You put the mass of the Higgs in by hand, and you say it comes from something else, and you leave it. And if you calculate all the extra quantum effects that come in quantum field theory and ask, what would we naively expect the mass of the Higgs to be, we're off by roughly this factor, which I think that number has a name. I just forget what it is. You all could figure it out. Are we in quadrillion? Anyway, it doesn't matter. Quadrillion, thank you very much. Okay, so it has a name even, so it's not so bad. And the reason is because as you go to smaller and smaller distances or length scales, higher energy, you discover that the vacuum appears to be fluctuating violently. The fields in the vacuum violently fluctuate, and that fluctuation actually naively should give an amazing amount of inertia to the Higgs particle itself. It does not. Here's a toy model explanation for maybe what it might be. Do I think it's this? No, I don't think it's this. Bizarrely enough, this is the simplest one to describe. And then I'll mention briefly the one we think may be slightly more compelling, a lot less easy to describe. Let's try to imagine extra dimensions of space. Extra dimensions meaning there are 3 spatial dimensions. There are 3 numbers we can parameterize every position in space, x, y, z, length, width, height, east, north, up. And what if there was another direction which was perpendicular to all 3? You can't picture it. Of course you can't. You live in 3 dimensions. And evolution has dictated that you don't picture such things, that you are used to 3 dimensions, and that is the infrastructure of how we operate. But now let's imagine that people live in 2 dimensions, flat land, as has been described many years ago. If you live in a 2-dimensional world, you can imagine that that 2-dimensional world, the surface, is embedded in a 3-dimensional world. And if somebody threw a ball at your universe, it could just pass right through your universe in principle. And what that would look like on the surface is just the part that the 2-dimensional universe has access to, which is a dot which grows into the full area of the cross-section of the ball through the equator and then back to 0. So if in case we live in 3 dimensions, but let's say there's an extra dimension out there, you can imagine hanging out with friends and then all of a sudden a ball appears, 3-dimensional object appears, it goes and then disappears. We haven't seen that. So that puts constraints on what the extra dimensions could be. Extra dimensions could be curled up. What does that mean? Well, we live in 3 spatial dimensions, but I remember as a kid thinking, what if it was like you went this direction and you went long enough and then you came back on the other side? And somehow that direction's connected to that direction. Well, some kids don't stop thinking about that. And you can imagine that there are directions like that. You can imagine it's true in our universe too, that it's in fact totally compact and space is connected in a 3-dimensional compact manifold. You can say fancy things like that. Or you can imagine there are extra dimensions, but their length, the total length that's wrapped around in a circle, is so exceedingly tiny that us big figures, we have no contact with it. We don't notice it. It's way too tiny. There's another direction, but it's all wrapped up on itself, and you can't see it. You can't experience it. Again, you don't understand it. I don't understand it. It's not something you can intuit. It's just something, but when you go to math and you write down the equations for a 3-dimensional situation, you can change the 3 to a 4, and then you can find out the consequences of that. So when you do that, it turns out that these are physically relevant, and you could create a type of universe that looks 3 dimensions, but deeply inherently is 4 or more. I'm just talking about space. Time is also a dimension. But if the dimensions are curled up, we actually already have very tight constraints on how big they can be. They have to be very tiny. That number. What's that number? All right. So a particle going in that dimension could go around the dimension. But particles are waves, which means they're constrained in a way. If you have a closed system, or if you say have the 2 ends of a line or a string are fixed, it tells you what wavelengths can fit on that string. And there are certain wavelengths that can fit in that loop around the extra dimension. So you can put waves around the extra dimension. But remember, waves and frequency of waves correspond to energy. And so we're these big blobby things. We don't notice the extra dimension at all. And so when you see this little packet of energy, which is a wave going around a circle, well, we think of it, we look at it and we think it's just a particle. And it's a particle that has the energy coming from the momentum in the extra dimension. And so when you add up the mass of the actual particle itself, plus the extra energy from going around the extra dimension, you get a much bigger mass. Your E equals mc squared gives you a much bigger m. You see it at a much bigger energy. And so what we would see at colliders is we wouldn't see some new pathway into a different direction. We would see particles of a mass associated with each wave. And so we would see this very funny spacing of particles corresponding to the inverse of the size of the extra dimension. And so people have constructed theories where the bottom rung is where the Higgs lives. So maybe there are lots of vibrations and fluctuations, but the stability of the physics within that extra dimension is such that you could have the Higgs living at the bottom, and then you could have a tower going much higher. And so we would, in that case, you'd see the Higgs, but you'd see a whole bunch of other stuff coming with it. The more popular or compelling theory about what is going on roughly at those energies of the Higgs, what explains the Higgs mass, is supersymmetry. Supersymmetry, sort of like an extra dimension, except that it's quantum mechanical and it's not continuous. I know that's not helpful. And here's a drawing, and that's not helpful too, because first of all, it's wrong. Second of all, I don't think you can get anything other than I don't know how to draw it. So that's, I think, all you can really get. But the difference in supersymmetry is that it would be an extra dimension, but you'd only get one package of superpartners. It can only go around the extra dimension once. It has something which is equivalent to what's called the Pauli exclusion principle, that particles of matter, like the electron, can't be at the same place at the same time. And that exclusion, it turns out, in this structure of space-time also doesn't allow a whole tower. Once you have one type of particle where it goes around the extra dimension at a certain momentum, you can't have any more. It's weird. But what that implies is that all the standard model particles could go around that dimension once, in a sense, and there's another state of matter where they have this higher energy. And so then people try to figure out, how are we going to picture this? And so then they say, well, there are particles, and then there are mirror particles or shadow particles. All these analogies are just horrible, but that's what they are. They're analogies. But the implication is that we discover these other particles, and that energy scale where they appear is associated with the energy scale of the Higgs. And so you take the standard model, you multiply by 2, approximately. There's some subtleties too. But when you do, it turns out that the quantum effects of the two sets of particles cancel. And so all that mess that happens potentially at very short length scales goes away. And this is just a property of a very deep and beautiful structure to the symmetry. And some weird thing is that in the simplest models that can describe nature, there's one or more possible particles that end up being stable and can possibly be the dark matter of the universe. But we have not seen it, and it might not be true. And if you go back to Kepler, you think, well, you know, he had a gorgeous description, possibly, of what it looked like, planets going around because of these beautiful geometric solids. I mean, they literally thought, the transition time was at Kepler, they literally thought the planets were embedded in spheres that were rotating around the Earth, was actually what they thought. And then they noticed from the data they had to correct it in epicycles and things like that. But he gave up on that theory because it didn't work. And so maybe, what if this is that? You know, you can always look back and say, oh, wait, maybe we're doing that, just like Kepler did. Another Feynman quote, never look back at history to see how a discovery was made, because your discovery will never be anything like anything else. That's why they're so hard, because you don't know even where they're going to come and what they're going to look like. But you could ask, in the same way that there are many planets and around many stars, there's nothing special about the planets going around our star, other than we're here and we love it. Does the Earth need a deep reason to exist to support life? Did something magical happen to put Earth right where it needs to be? We believe now that there are on the order of 1 trillion planets in our galaxy alone, and 100 billion galaxies in the observable universe. What are the chances one of them is going to be in a nice spot? Well, pretty good, I think. It's not a theory that people are working on. Why did our Earth end up in the right spot? No, we look at a distribution of possible planets. There are plenty to choose from. What if our entire visible universe is a random accident? And that there are many, many, many universes with many different laws, and the numbers come out in different ways in different times, and the Higgs is not explained by some deep mathematical theory. It's actually, where it is a random accident. It's just what it looks like in our universe, and it was necessary for it to be tuned in such a way that we could live. Many of the universes are boring, don't have any structure to them, but if things are just right, perhaps our universe is right. Now, it turns out you would need this many universes. What's that? I gotcha. Okay, you need that many universes to make this a plausible theory. But who knows? We don't know. We have our observable universe. The biggest struggle with this is how do you test something like this? This is a struggle that some people think about. You reject the idea, say, oh, this is crazy, this is philosophy, blah, blah, because you can't test it. But there's still the inherent taking steps and asking, could something like that be true? And does that tell us something about when laws of physics are pointing to something fundamental and when laws of physics are, in fact, historical accident in the location we are looking at them? Now, what? Okay, what's the name of that number? It's what? 10 vigintillion. Woo! That's a measurement error. We will get back to it. I'll let you look after. In defense of supersymmetry, where you just double the number of particles to try to explain something, which may be better than vigintillion universes, antiparticles were something that was posited by Dirac and discovered. Now we know they exist. We can create them. We see them in cosmic rays in the universe. But they were necessary to deal with crazy numbers coming out of the beginnings of understanding quantum field theory. So you have to learn to live in uncertainty if you're a physicist. You cannot predict where the big discovery will be made. Most of us will be wrong, and possibly an entire generation could be wrong about what's the big discovery, what's coming next, what is the deeper explanation. But you need many people pushing in all directions until we get there. I can make historical arguments for both of these possibilities, and they both may be completely wrong. They both may be true in some other aspect, but we don't know. Doing physics means that. Something human beings, I think for sanity's sake, they put labels on everything and are certain about so much more than they should be. And physics is a place where you really do need to take moments where you don't know what's going on, you allow something you think is true to be thrown out, and you start exploring what could be true. Or you try to extrapolate your rules into a place maybe you don't think you're allowed to go. It's a lot of that. And then when you have a project, then you're certain that's the greatest project in the universe, and you work on that for a couple of years. But you have to back up. And I think it's a beautiful lesson, not just for science, but for life, which is you see a lot more possibility if you can step back and simply be uncertain. So I'll stop there. Thanks.